Good evening. So before we start, Stephen, I understand that you're in chemistry now this semester this year.
Yeah.
Okay, so kind of tell me what you guys are learning right now.
We've done a couple labs before, and I think we're doing of the frequency, the energy, the wavelength. I think that's what we're doing right now.
Okay. Jeffrey, are you in class right now too?
Fine arts.
You're in fine arts?
Yeah.
So you're not in chemistry?
Yeah, I'm in chemistry.
Oh, okay. So what are you learning right now?
Oh, we're learning like so-called like
Say that again, I missed it.
yeah like
You can chat it out if you want to. Write it in chat.
yeah like the atomic number, like the periodic table.
Okay. Well, that's interesting that you both are on such different spots. Okay, so we're having class according to Ms. Jenny until November 16th. I have acids and bases I was going to teach you, and after that, really all I teach for first year chemistry is a little thermo, which is heat transfer, calorimetry. And there's no rush to do that. You're not going to get to that anytime soon. So each week as we start our meeting, if you have something that you need to review from your current class or anything like that related to your current class, let's take the opportunity to review that topic, answer any questions you may have. And so we'll start that now. Do either of you have any questions about what you're currently doing in class or anything that we need to review?
Can I take a look at my notebook for chemistry?
Yeah.
Okay.
Jeffrey, is yours pretty easy so far?
Yeah, I think they probably like started a new unit yesterday. Yeah, but I was not there.
Okay, so you took a test last week.
Yeah.
Did you do well on it?
Yeah.
Good.
I think I don't really have questions for the frequency and calculating energy right now.
Okay.
It's not that hard, but as we get into it, if I've got questions, I'll ask during class.
Okay, so you remember it from a few months ago when we did it?
Yeah, I can't remember on the top of my head, but learning it in school, I felt it was much easier than first time learning it.
It always is.
Mm-hmm.
Yeah, and that's why your parents put you in this, so that when you do it at school, it's all going to seem easier, I hope. All right, well, if that's the case, then we'll get to our normally scheduled stuff for tonight.
And also, I have to leave at 8 o'clock tonight.
Okay.
So if there's anything that I missed, can you like put it on Google Classroom or
Yeah, I'll be posting the video tonight because Keelan's not here.
Okay, yeah, thank you.
Mhm. All right. My memory's a little fuzzy. I checked our my stack of recycled papers from last week, and according to my stack of papers, this is where we stopped. Is there any disagreement with that? We have not done this yet. Okay.
I'll take a look at it real quick.
Okay.
No, we haven't done it.
Okay. Good. My memory's not as bad as I think it is. All right. So last week at the last 30 minutes of class or so, I introduced you to what's eventually, it will be a while, but will eventually become the most important unit for your high school chemistry, and that's molarity, capital M. The formula for molarity is moles per liter. This is a concentration unit. It tells you how much solute you have per liter. And then we also did a little equation because we know that when we dilute something, we just add water to it. So the moles of solute doesn't change before and after, just the water. And because of that exists, we have a proportionality that we just call the dilution equation. The molarity times the volume equals the molarity times the volume under new conditions, new volumes. And that's an inverse. So I just had a few problems. I figured I would remind you, work a couple, give you a chance to dig into it a little bit, and then we'll get into acids and bases. Acids and bases are going to require us to use molarity, so we've got to review it. So number one, how many liters of solution are needed? So that's just a fancy way of asking for volume. To make a solution that's 0.5 molar, and we have 2 moles of barium chloride. That's a fairly straightforward plug in and solve. Our moles go on top, and our volume is in bottom. And that's what we're solving for. The reason I put this question first as a review is because I've done this a long time, and I know that when the variable is in the bottom, students' math skills erode. So if you rearrange this equation, the volume comes out to be 2 moles divided by 0.5 molar, which is moles per liter. So just rewriting what molar stands for. It's an inverse proportion, just swapping places. And so we work the math on that now. That's going to give us 4 liters. Okay, and number 2, we're going to calculate the number of moles. This is pretty easy. So moles are unknown, and we have the volume this time and the molarity. Well, that's pretty simple. Moles is my unknown. We've got 10 liters. That's just a quick cross multiply, and we've got it solved. That's going to give me 20 moles. All right, so that's just kind of playing with the equation. As we get into number 3, we're going to have to bring back some old skills, because this time the solution, the solute, is given to us in in grams, not moles. So we can't just plug it in directly. But we do have the final volume in liters, so that's good. The first thing we're going to have to do here is go from grams to liters. 42.5 grams of sodium chloride. Oh, I thought my marker was healed, but it is not. I got excited for nothing. So grams to moles. All right, so remember sodium chloride is NaCl. So that's 58.5 grams per mole. Okay, so we had, in this problem, we had to do a separate mole conversion to go from grams to moles to get, in this case, the numerator, the moles of my solute. Now that that's over, we can do the molarity equation. So it wants the molarity. We just found the moles, and we were given the volume. So the 2 sig figs, that is going to be, it's late at night and I'm getting old, so calculator, 0.073 molar. So not much, not very much. All right, let's skip number 4 for the sake of time. And let me give you guys a couple of minutes to work 5, 6, and 7. 6 and 7 may be a little repetitive, but it's not going to hurt you. So 5, 6, and 7. All right, I put the answers on the screen. Are we close to being done?
I'm done.
Okay. Jeffrey, are you done? All right, I'll take that as a yes. All right, so any problems there?
No.
Okay. All right, so like I said, that's a pretty common tool here. We'll need it for pH calculations here. Maybe tonight, maybe next week. As I said in the post, anything that we don't get to tonight with acids and bases, we'll get to it next time. I never thought we were going to be able to do the whole thing tonight, for sure. All right, also related to acids and bases is the naming system. We did name acids and bases a month ago, 2 months ago. I can't remember anymore. It's been a little while. And so it's not going to hurt us to review the naming system for acids real quick before we dive into acids and bases. I just had a brainstorm of sorts. So let's talk about bases as well. So for what you're going to do in high school, bases typically have an OH group, a hydroxide group, in an ionic bond. So example, sodium hydroxide, calcium hydroxide, not something like this. That's an alcohol. That's covalent. So that won't be a base. So that's kind of what we want to look at when we talk about bases for chemistry. And since we're just talking about ionic hydroxides, the naming system for bases is exactly the same as how you would name it in the ionic naming system: sodium hydroxide, calcium hydroxide, and so forth. For acids, we wished it was that easy. Acids get a whole different naming system for some reason. I don't know why. They do. But there are two types of acids. The first type is binary, which follows the generic formula of HX. Okay, so we have a hydrogen cation, and then the anion is going to be some sort of monatomic anion. So some non-metal element. When we name binary acids, we're going to use the hydro prefix, and that takes care of the H, short for hydrogen, hydro. Then we're going to take the root of this element X here. If it's chlorine, we take chlor. If it's sulfur, we take sulf. And we're going to change the suffix to ic. All binary acids end in ic. I call them hydroblankic acids. That's kind of what I learned to myself, hydroblankic. So when we name them, really, it's our job just to fill in the blank. That's it. I had an example here somewhere, HBr. So really, we get the hydro, we look at the bromine, so that's our root, brom. So that's all we put in the blank, hydrobromic acid. That's it. That's literally all there is to it. And there's not a lot of these, not a lot at all, because we don't have that many monatomic anions. We have the halogens, we've got like sulfur and selenium, a couple more. There's not a ton of these. There is one exception. HCN is considered a binary acid, even though it is technically ternary, got 3 elements. But it does not fit very well into this group down here. So because of that, instead of coming up with a third group of acids, they said, nah, let's just, this is cyanide. So it already ends in IDE like chloride and sulfide. And they said, yeah, let's just go ahead and throw it back into this pile and we'll change I to ic. So we'll call it hydrocyanic acid. And it meets most of the criteria of the other ones. It's just got too many elements in it. The other group of acids are much more pervasive. There's more of them. These are called ternary acids. It really depends on what language your teacher will use this year. You will be doing this. Ternary acids, I prefer the name oxyacids. I've also seen it written as oxoacids, whatever. Basically, this just means hydrogen, still there, always, and then polyatomic ion instead of a monatomic ion. The naming system is actually easier. So we're going to take the polyatomic ion, sulfate, chlorite, whatever it is, and we're going to change the suffix. If the suffix is ATE, you're going to change it to ic. So that's twice we've used ic. If the polyatomic ion ends in ITE, ite, you change the suffix to OUS and then add the word acid. The example I gave here, this is CO3 as carbonate. So it's real helpful if you have the polyatomic ions, mostly memorized. That makes it very quick. Carbonate, and so you just change the ate to an ic. So that's carbonic, and then we add the word acid. That's it, easy peasy. All right, so on the back, I have some practice. I know you guys don't like to talk out loud, so let's do it this way. I'm going to give a moment and let you answer the questions sort of silently, and then I'll give the answer so we can kind of work a little bit faster pace and also give you a chance to think about it before I start blurting out answers. We'll do the top section first, and we're going to answer this question here because this is really important. This is a really important thing to do. When you're looking at an acid formula or name, decide which type of acid it is, binary or ternary. So go through this list and put a B next to the binary ones. All right, I hope you put a B here and here and here. And so we'll just assume that anything we didn't put a B next to is going to be ternary. So let's go ahead and name these binary acids. Remember hydroblankic. So think to yourself, what would the name of this acid be? Okay, I hope you're thinking hydrofluoric. I'm not going to write the word acid every time. I'm just going to write the main name. All right, this was our example. We've already done that one, hydrobromic. And then to yourself, go ahead and name HCl. So hydrochloric. All right. That means the other acids here are ternary or oxoacids. So it's all about identifying the polyatomic. All right, so we're going to do this the same way, except I'm going to get you to silently to yourself name the ion that you see, and then from there, get the name of the acid. So first, let's see if you can identify that, NO3. All right, I hope you said nitrate. And then from there, nitric. Again, I'm not going to write the word acid every time. This was our example. Carbonate becomes carbonic. All right, now here's a tougher ion, PO3. Think about what that ion is called. That one is phosphite. And this one's a little bit of a tougher deal to get the name, because phosphorus, it's phosphate and phosphite. But as soon as you start making this, now it bounces back to phosphor. So the root changes a little bit on you. And this becomes phosphorus acid. So sulfur and phosphorus do weird things with their roots. I don't understand it. All right, so see if you can identify ClO4. All right, I hope you identified that as chlorate. So this acid here, sorry, that is not chlorate, that is perchlorate. So this acid will be perchlor. I didn't do anything different to the per. It came as per, it's leaving as per. Perchloric. Eights become X. And then probably the hardest one here is the BrO2. Identifying what that one is. I'll give you a hint. It's analogous to ClO2. So that is bromite. And that will give us bromous acid. All right, let's do a few of the formula writing from the name. So the key here is to dissect the name and get your ions. We already know that in every one of these, hydrogen is the cation. Your job is to get the anion. And the anion comes from the name. Just like before, we need to decide which of these are binary. So again, go through and put a B next to any of these in this grouping that are binary. There's a real easy, obvious clue to pick out the binary acids from their name. I hope you found it. You're looking for the hydro prefix. It's real easy to pick out. Anything with hydro is binary. That means each of its anions are going to be monatomic. When I see iodic, here I know it's from the element iodine. And we just, go back to the periodic table, figure out the valence electrons, and then how many or what charge iodine is going to have. So we know halogens are -1. And down here with cyanic, okay, so that's the exception. That's a weird one. That comes from cyanide, which is a polyatomic. Hydrochloric, all right, so it comes from chlorine. We know that's a halogen. And then sulfuric, so that comes from sulfur. Sulfur has 6 valence. We know it wants to gain 2 and be -2. So that's kind of the key for going from name to formula. Getting those ions, those anions out of the name. Once you do that, you just put it together. +1 -1, high, +1 -1, HCN, +1 -1, HCl. And down here it's different, +1 -2. So this formula is H2S. All right, so that means the rest of these are ternary or oxyacids. So again, the key is dissecting the name, using that suffix to work yourself backwards. What polyatomic did it come from? Remember, eights become icks. So an ick came from 8. That means this is sulfate. And if you had your polyatomic ion list close by, you would grab that off. Okay. Here, nitrous. Remember, us comes from ite. So this is nitrite. And from our list, we know it's NO2. Acetic comes from acetate. I know it sounds a little different, but acetate. And so we know that is C2H3O2. Chloric comes from chlorate. This one's a little harder. This is not one we do a lot of. Oxalic comes from oxalate. And you would probably do need your list for that one, but that's what it would be. And phosphoric comes from phosphate. And that's the hard part. Now it's just putting them together. Essentially, if you haven't figured it out yet, it's however many your negative charge is, you need that many hydrogens to counteract it. So if sulfate's -2, you're going to need 2 hydrogens. If nitrite's -1, you'll need 1 hydrogen. And down here, phosphate, you need 3. So acetic acid, 1 hydrogen. Chloric, 1. Oxalic, we need 2. And that's it. All right, that should have been a review. Any questions on that while I transition to the some base stuff?
So for ternary acids, we don't name the hydro up in front of the polyatomic ion.
That's right. That's the biggest difference.
Okay.
Okay, so as far as notes go, I don't think there's a lot that I would suggest you write down from this PowerPoint. Instead, what I would suggest you do is if you write anything down, it's going to be these definitions if you want to, but I also included them on the next slide. So if you just want to print them out, you can do that. Let's start here with some rudimentary properties of acids and bases. This is like middle school level question. It used to be the old tax level stuff, but we'll ease into it. So an acid, chemically, these are natural chemicals, both of them. And your body actually evolved a detector test for acids and bases. And both involve being like a hunter-gatherer. In nature, things that are acidic tend to be fruits that are not ripe yet, because there's still the juices inside of them haven't reached their full biological purpose, I guess, and so they are a bit acidic. And you don't want to eat that. Like persimmons comes to mind. Raw persimmons are about as sour as you can get when they're not ripe yet. And that's if you eat them and they're not ripe, then that tends to upset your stomach. And so that's kind of like an early warning system for your body. On your tongue, you have taste bud receptors specifically designed to detect sour. Well, all that is an acid warning system. If you were to drink hydrochloric acid before it melted your tongue off, it would taste sour to you first. And similar with bases, your tongue has an early warning system. Bases are a little bit more subtle and widespread in nature. They're in a lot of plants. They're called alkaloids in nature. But a lot of plants have these chemicals as a deterrent for insects and other animals that eat plants. So it's kind of like poison. A lot of plants are poisonous, and that those poisons taste bitter. So again, your tongue has bitter receptors on it. Those bitter receptors are designed to bind to basic bases in the chemical structure of bases, because you need to spit it out. If you eat something that's bitter in nature, it's probably poisonous. You need to get rid of it. So acids are sour, bases are bitter. There's a natural chemical called litmus. It's a bit of a plant dye, I guess, for lack of a better word. And the chemical in litmus has a unique property of changing its shape, its molecular shape. In the acidic environment, it reflects light a certain way and looks red. But if you put it in a basic environment, the shape bends and changes a little bit, and it makes a different reflection. Now it looks blue. So acids in litmus look red, bases in litmus look blue. And a final one is also that bases feel slippery. One of the main ingredients in soap, especially bars of soap, is lye, L-Y-E. That is sodium hydroxide, which is classic base. And these bases, as we've learned, not just sodium hydroxide, but the other ones in other hydroxides are pretty difficult to dissolve. Some of them we even classified as being insoluble when we did double replacement reactions. Well, when you take a shower or a bath and you're using tap water, your tap water contains calcium ions, magnesium ions. And so essentially you're forming lots of hydroxide precipitates in the shower. And those feel slippery. That's what makes soap feel slippery, all those hydroxides that are not very soluble. So I've always remembered it as blue bitter bases, a little alliteration there to have to remember it, blue bitter bases. So by nature, acids and bases are what we would call ionic. It may be a bit too simplistic for some of them, but at a minimum, they're very polar, very polar. So these acids and bases are going to be treated like ionic compounds. So when you dissolve them in water, they're going to dissociate in water. To be an acid, you must be aqueous. Okay, HCl by itself is not hydrochloric acid. HCl by itself is a gas, and it's called hydrogen chloride or hydrogen monochloride. Only when you put that gas in water and it dissolves can it be called hydrochloric acid. So the aqueous part is a necessity for these. These reactions must take place in water. We call these reactions neutralization reactions, acid-base reactions. They are indeed just double replacements. We've known about acids and bases for longer than we knew how acids and bases worked. So it's been an evolution in trying to describe their behavior. The first definition to try to figure out what's going on was made by Arrhenius. He's actually the scientist who discovered ions. And his definition was a little exclusive. It didn't allow some things to be acids that should have been. So over time, we developed a new, more inclusive definition of acids and bases. And then even past that, over some more time, we realized some things are being left out. And so we come up with an even more inclusive definition of acids and bases called the Lewis. Yep, same Lewis from Lewis structure. Gilbert Lewis, probably America's most famous chemist, pure chemist. So the definitions, the Arrhenius definition first, since it was the initial one, says that acids are any substance that increases the concentration, the molarity of the hydrogen ion. Okay, so if we can simplify what that means a little bit, these are going to be anything that when I dissolve it in water, the hydrogen will break off or dissociate to give me H positive. Well, all those acids we named would do that. And one visual clue would be that there's a H in the front. So a lot of people oversimplify the Arrhenius definition to say anything with a hydrogen in it is an acid. Yeah, not really. Anything in with hydrogen in the cation position is a Arrhenius acid. And then he said bases are anything that increase the concentration of hydroxide. So in other words, when you dissolve substance in water, the hydroxide ion is dissociated and causes the molarity of it to go up. So Arrhenius essentially said acids have H, bases have OH. And that seems like a very broad definition that would cover a lot of stuff, but it left a lot of stuff out, like ammonia, NH3. It turns out that ammonia is a base. Well, according to the original Arrhenius definition, ammonia wouldn't be a base because it doesn't have hydroxide in it. So things like that are what led the second definition. This is actually the one we use the most in chemistry, even in AP chemistry. This is called the Bronsted-Lowry definition. These are two chemists that work together. They defined acids and bases more on how they behave and less on what they look like or what they have. So the definition of acid is that acids are proton donors, and a proton is an H positive. So proton donors. In a reaction, an acid will give you an H and say, here, take my H. And then bases are proton acceptors. So if acids are giving their H's away, you got to have something to take it, and that's what bases are. And then, as I mentioned, over time, Lewis came up with a definition. It's a little bit more complicated. I don't really think it's worth too much of our time to over-explain it. But basically, Lewis said that acids are going to be those substances that accept electron pairs. So he based it more on his Lewis structures and how you put Lewis structures together. Acids are electron pair acceptors, and bases are electron pair donors. If you are an acid according to Arrhenius, then you fit all of these. Okay, if you're a base according to Arrhenius, you fit all of these. So every one of these definitions gets more inclusive. If you are an acid according to Lewis, then it's possibly you're not a Bronsted-Lowry. You're not an Arrhenius. One example is a BF3. BF3 is an acid. There's not a hydrogen to be found in BF3. But according to Lewis, it is. So that's just one example. But we're going to hang our hat on this middle definition, Bronsted-Lowry, proton donors, proton acceptors, and I'll be coming back to that. Questions so far?
So I think is acid and liquid. What is the base? What does the base look like?
They're both going to be solutions. Most of them are just perfectly clear. If you had a bottle of an acid and a bottle of a base sitting on a shelf, you couldn't look at them and tell the difference.
Okay.
Yeah. In the solid form, you can get these bases are easier to form solids because they're ionic. The acids, no, they're kind of hard to get into a different state of matter. Some of them would be gases like HCl or HBr. Within the oxyacids, they don't even exist outside of solution. So yeah, we don't even have those to worry about.
So when it says base or proton acceptors, if they accept proton, are they a cation?
They could possibly become a cation. That's right.
And acid is possibly an anion.
It will end up as an anion. It doesn't start as one, but it will end up as one.
Okay.
Yeah.
Thank you.
Mm-hmm. All right. So I think I've gone through most of this. Bronsted bases must have a non-bonding pair of electrons. We will come back to that. We'll look at some structural difference. But here's another vocab word for you. Substances that can act as both an acid and a base. Yep, there are those. And they're called amphoteric, like an amphibian. Same Greek root. Amphibia means two lives, in water, outside of water. So here we're talking about chemical substances that have two lives, as an acid and as a base. The most common example of an amphoteric substance is water. Believe it or not, water is an acid under certain circumstances, and it can be a base in others, but it can be both. So let's take a look at an actual reaction, and let's sort of analyze how protons are donated and accepted. So in the top reaction, we're using water. So this is an amphoteric example. Water is an acid. No, water is a base in this first one. HCl is the acid. So we're going to see the Bronsted-Lowry effect take place. An acid is a proton donor. So it's going to give this H to the water molecule. Then the water molecule accepts it, and it forms what we call the hydronium ion. So like you said, it's going to be a cation. And that leaves behind lonely old chloride. So that is a Bronsted-Lowry acid. Now, a base like ammonia is going to accept a water. Now water is going to become the acid. So water is going to donate or give a hydrogen to ammonia. And that causes it to become NH4, positive. Again, yes, cation. And that leaves behind from water the hydroxide. Okay, so we fulfilled the Bronsted-Lowry definition. And as you can see here, we made hydroxide, and that fulfills the Arrhenius definition as well. Acid-base reactions are your traditional double replacement for the most part. Acid and base can get a little bit more tricky, but not in first-year chemistry. So almost everything you're going to see, I hate to use the word always, but almost everything you're going to see is going to be straight up double replacement ion swaps. That's it. You've done a ton of these. So when that happens in acids and bases, we have two things that are always constant. There's always an H in the acid, and there's always an OH in the base, which means one of our products will always be the same, and that's going to be the formation of water. So when we do our swap, one of our products will be water, and the other will be a salt. So remember, a salt is just an ionic compound that is soluble in water. Sodium chloride is an example of a salt. I know we kind of use the word salt kind of freely when we talk about sodium chloride. It is just a salt. Any other soluble ionic compound is a salt. So they're double replacement. We most often call these neutralization reactions. And when we say that, we're kind of referring to their pH, which we'll get into. But they neutralize. That implies that they are opposite each other in terms of their chemical reactivity. When we get to neutral, we are at pH of 7. Stoichiometrically, what that means is if we have neutralized one of these, then you have equal moles of acid and base. And that's very important, equal moles. Let's see, I don't have a ton of slides in this, I promise. So Stephen, whenever you have to go, just go, okay, we'll have this video put up soon.
Yeah, I'll probably leave at like 8:05, 8:10.
Okay,
like
that's fine. All right, so we'll do a little bit of practice here with conjugate acid bases. This may not make a lot of sense until we do some on paper work with it, but the thing about acid-base reactions, there are a great deal of them that don't just go from reactants to products and stop. The products will actually start reacting together and send the reaction going backwards. So as you can see down here in this example, we have generic acid HX in water. So an acid and a base. So we donate the H to water and it becomes hydronium. And we're left behind with X -1. Now, if you can think about what these two are going to do, well, now H3O can give a hydrogen right back. And it will reform HX and it will reform H2O. So in the reverse reaction, the H3O has become the conjugate acid. And we say conjugate just to let us know it's on a different side of the equation. And this becomes the conjugate base. So we have what we call conjugate acid-base pairs. The acid is always paired up with its conjugate base. HX is an acid. When it does its duty, the residue, if you will, for lack of a better word, is the X minus, and that's going to be the conjugate base. So you're going to be dealing mostly this year with strong acids when you eventually get to the section. There's a few reasons for that. Number one, these acids will 100% dissociate in water, and that's important because if they didn't, then we would have to bring an additional chemistry skill of working with equilibrium, which is something AP chemistry students do a lot of. Okay, if you go to AP Chem, you will eventually deal with weak acids, but strong ones don't. They 100% dissociate just like NaCl or any other cash and GS solid. Also, their conjugate bases are pretty pathetic. So we don't get a lot of that forwards and backwards reacting stuff with strong acids. In fact, we don't get anything. The conjugates this is kind of a one direction reaction with strong acids and bases. At some point, you should probably memorize the 7 strong acids, whether it's this year. Memorizing them now is probably not that helpful because you will forget. But maybe when you get to your unit this year in class in the spring, you'll want to memorize these 7 strong acids. There's not many. It's just the 7. And everything else is weak. Hydrochloric, hydrobromic, hydroiodic, and then nitric, sulfuric, chloric, and perchloric. You've heard of most of these. The most notable exception, you're probably wondering, where the heck is HF? Like fluorine is stout. You would think fluorine is a real strong acid. It is not. Hydrofluoric acid is a weak acid. And if you know anything about hydrofluoric acid, you know it eats through glass. That doesn't sound very weak. Don't confuse this definition of strong with reactivity. Weak acids, if like HF, can eat through glass, but that just means they don't dissociate 100%. So that the definition of strong and weak here has nothing to do with chemical reactivity. It's all about dissociation, and there's only 7 that do it 100%. So I'm not going to go through weak because it's kind of an AP topic, but I will point out some of the most common weak acids that you'll come into contact with. Hydrofluoric, acetic, and those two are by far and away the most common that you'll see in chemistry class. Others that you may hear of, that hydrocyanic, formic acid, which is in ant bites, benzoic, propionic, probably not that much on those, but definitely hydrofluoric and acetic. Okay. Let's take a pause in PowerPoint for a moment. We've been doing PowerPoint for about 10 or 15 minutes. And let's go back and let our brain soak in this idea of conjugate stuff. And we'll come back. We'll judge the time. We may work this out to where we start pH on a fresh note. So let's work with some of these conjugate acid-base pairs. I think I've done a decent job in the PowerPoint of kind of telling you what they are. So if we flip over here, let's take a little practice with moving in our head, moving these things forward. All of these are acids according to the instructions. Okay, just what the instructions tell us to do. So what would be the conjugate base if all of these are acids? Well, remember, an acid donates a proton. It gets rid of an H. So if I did that here, I would have NH2. And what we also have to remember is that hydrogen is going to carry a positive charge with it. It's a proton. It's a proton donor. So that means I will now have a negative charge. So that's the conjugate of ammonia when ammonia is an acid. So here's the hydronium. All right, so if we donate an H, that leaves behind H2O. We take away a charge as well, takes me back to 0. All right, I know you're getting the hang of it now, so think about what this one would be. And I hope you said SO3 with a -2 charge. All right, with that in mind, what would this one be? Ammonium. Take away an H positive, and we're left with NH3. And that one, what would that one take us to? HPO4 -2.
So the superscript is applying to the whole
Whole thing.
whole thing. Is not just one, just not one element, right?
That's right.
Okay. And I also have to leave right now.
Okay, I'll see you next week.
All right. See you next week. It when are you posting the video on?
When I get done, it'll have to convert, and that takes a little time, and then I'll have to upload it to YouTube. So I'll try to do it before I go to bed tonight, but it'll be at least some hours before it gets done.
Okay, no problem. All right. Thank you. See you next week.
All right. All right, so in the conjugate acid, what is the conjugate acid if these are bases? So remember, bases are proton donors. So they got to come from somewhere. So we're just bringing them out of the ether here. So if I start out with PO4 and I add an H to it, it's going to be HPO4. But I'm also bringing that +1 charge with it. And so -3 now becomes -2. It's less negative. Okay, ammonia has no charge, so it's a base. If I bring an H positive into here, we add it all together, it becomes NH4 and now an extra positive charge. I don't know what that is. So here this is called bicarbonate or hydrogen carbonate. Bring another hydrogen in, that's H2CO3, and that positive charge gets rid of the ions. So this is now a neutral acid. Let me rephrase that, a neutrally charged acid. And this one looks kind of goofy. Where would we add this? So we would add that, this is beyond the scope of 10th grade chemistry probably, but we would add it to the end. Because structurally this carbon is already full. And all those rules we learned about Lewis structures we can't violate. This carbon can't have more than 4 pairs. So it's got to be on that side. All right, so in Roman numeral 3 here, complete the following acid-base reactions, assuming only 1 hydrogen. So we're just going to, swap, donate 1 hydrogen back and forth. Identify the conjugate acid-base pairs by writing them below the equations. Well, let's take a look here what we have. If I had to name these, I would call this phosphate, so phosphoric acid. So that's going to be my acid. And sodium hydroxide here, that must mean it's the base. That's not, what am I? That's ammonia. I don't know where in the world I said sodium hydroxide, but that's ammonia. And so now that we kind of know who's who, we're going to execute the Bronsted-Lowry definition here. Phosphoric acid will donate, and so we will make ammonium ion. And that leaves behind over here the conjugate of H3PO4, which is H2PO4, which now has a negative charge. Now, if we can ignore that, and let's examine what these would do if they were to react and go backwards. Your positive charges are now going to be your donors. It's hard to donate a proton when you're negatively charged, but if you're positive, you have some extra charge to get rid of. So this will be the conjugate acid, and this will be the conjugate base, and they'll be paired up like this. All right, in the second example here, we have the carbonate ion. That's not very helpful. And sulfuric acid. Okay, well, that's helpful. That's an acid, which must mean this is a base. It is a weak base. That's why they're not ending in hydroxide. And for the sake of this practice with conjugates, it's easier with weak stuff. All right, so do your acid duty. So that means donate a hydrogen to carbonate. So it'd be HCO3. And that positive charge reduces the charge of the ion to -1. And that leaves behind HSO4, also with a negative charge. So this was the acid. This is paired up with this one. So that must mean this is the conjugate base. Carbonate became this one, so this is the conjugate acid. All right, I think I just made an executive decision. We'll finish up a few more of these, and then we'll do the reactions, and we'll start pH fresh next time instead of starting it tonight. All right, so for 5A through D, the directions are kind of simple. Instead of doing anything, you're just visually looking at these and identify the pairs. So like I did on the previous handout, draw one of these little connectors to them. So take a look at this one and see if you can find the acid and the base. So it's a little bit difficult. You have to look at the products to see who gave a hydrogen and who took one. To me, it's easy to notice water became hydroxide. So water gave, and that makes it the acid, and that makes this the conjugate base. So those two are a pair. So we know by default then what the other one is. We don't even really have to think about it that hard. If you get one, you know the other one. But we can see here that this took the hydrogen, there it is right there, and became neutral. All right, see if you can do the same thing for B. All right, for B, Here it starts out with a hydrogen right in front. That's kind of a pretty good clue. Let's see if this one indeed gave that hydrogen up. Yep, it looks like it. So that is indeed an acid, and this will be the conjugate base. That means this is the base and this is the conjugate acid. I've always found it a little easier to identify acids than bases. Although over time, you will start recognizing when you see nitrogens in organic molecules, they're bases. Do you remember in DNA when you learned in biology, you know, DNA is made up of a sugar, was it phosphate, sugar in a nitrogenous base, I think is how they word it. So that's because in organic, nitrogens tend to be basic and they accept protons just like this. Happens in your proteins, happens in your DNA. All right, so looking at this one right here. This one is a bit more challenging. So it looks like this sodium here is causing us some visual anxiety. So let's just take it out of the picture here. And now without the sodium there, is it more obvious? And I think you would agree that it is. So the hydrogen is coming from here to here to make the H2. So this is my acid. And this is, believe it or not, my conjugate base. Wait, dumb. Nope, I got it backwards. I drew it right here. Donating, so that is my acid. This is my base. Had it backwards. It's pretty sad when you draw it right and then you get it wrong. And one little clue there as I was finishing my work was like, wait a minute. This is sodium hydroxide. That's the very definition of base, having a hydroxide. So there's no way I was about to put a Ca right here. And so that kind of clued me in that I had made a mistake. All right, and then finally, a much more straightforward one here. So that looks complicated. Let's check this one out. Water. Oh, okay, so that changed. So that means water gained a hydrogen to form hydronium. So those two are a pair. So this time, to me anyway, it was a little easier to identify the base. This is the acid, and this is the conjugate base. We do see over time that anions are basic, cations are acidic, little clues that you pick up on over time. All right, I want to move on from that. We may revisit that as a warm-up next time, so I'm not going to get rid of that. Put it right there. So what I wanted to do for the rest of the time tonight is look at just more straightforward 10th grade chemistry, double replacement. This is how we do it, acid-base reactions. So as I mentioned before, we do call them neutralizations, but they are double replacement. These type are double replacement. Come on, focus. We ain't got time for you. Well, apparently we do. Okay, so if we know these are double replacement reactions, then we don't have a lot to worry about in terms of executing the reaction. We know that we have the double partner swap, we have cation, anion, cation, anion. And it turns out that everything here is indeed +1, -1, +1, -1. So we're just going to literally swap partners, just swap them around. So sodium will go with iodide and we'll make NaI. And then hydrogen will come over here and form a partnership with hydroxide, in which we normally write as water, HOH. Remember on the slide, I said the products of a acid-base reaction are always a salt and water. And in this case, our salt is sodium hydroxide. Now, if you can think back to your double replacement reactions, I know it's been a while, a month or more. Yeah, way more than a month. We said that when we do double replacement reactions, we have to have what's called a driving force, because everything here is aqueous. It's all dissolved ions. And if we just form these products and they stay as ions, then nothing really changes. So like we spend a great deal of time with precipitates. Precipitates are what we call a driving force. Something changed, we get a solid, and that drives the reaction to completion. Well, in acid-base reactions, the driving force is the formation of water, which we would consider a weak or non-electrolyte, really. And that means that the salt is not always, but very commonly aqueous, but we would check that with cation Gia. Gia, group 1, so soluble. Everything's balanced. So next we have carbonic acid, and we're going to react that with strontium hydroxide. So there we go with hydroxide again, start to see it more. Aqueous, aqueous. All right, so now we do our swaps. Strontium is, let's do this, +1, carbonates -2. Strontium's an alkaline earth metal, it's +2, and hydroxide is -1. Now, just because this is a 2 does not mean when you swap it, it remains a 2. It may be, it may not be. We got to balance the charges. Strontium is +2, carbonate is -2, so this will give me SrCO3. And then I get H, which is +1, with hydroxide, which is -1. So the compound here is just HOH, or water. Not H2OH2. No, water. And that's a liquid. And now we can go back and balance it. So we need 2 H's, we need 2 hydroxides, so we put a coefficient. So we balance it with the coefficient, not with extra subscripts. All right, the only thing we're missing here now is, what is the state of matter for this one? This is a salt, but it is, according to our solubility rules, an insoluble salt, and it would be a precipitate. So we kind of get 2 driving forces in this reaction. We get the acid-base water formation, and we also get the precipitate formation. All right, another example, calcium hydroxide plus phosphoric acid, aqueous, aqueous. All right, let's take a look at our charges. Calcium is +2, hydroxide is -1, hydrogen's +1, and phosphate is -3. So when we do our swap here, calcium with phosphate, well, that's a big one. We're balancing a 2 and a 3. So we'll get calcium phosphate, which is very insoluble. And then hydrogen hydroxide, so water again. And balancing this one requires a little bit more effort as well. We've got, well, 3 calciums. So we're going to need 3 there. 2 phosphates. We'll need 2 there. So that gives me 6 hydrogens and 6 hydroxides. So remember that water is HOH. I need 6 hydrogens, 6 hydroxides. So we'll put a 6 in the front. Okay, well, what I had planned on doing at this point was giving a little time to work those reactions. So I guess, Jeffrey, you're the only one on video. So if you want to, we can stop the video and I can, or you can get off and I can just do the answers. Or that way, whoever's watching the video can just hit stop and whatever you want to do. What do you think?
Like the videos.
You want to do the video?
I can do it by myself.
Okay. So if you want to go ahead and log off, you can. I'll see you next week. I'm going to just work to keep this real quick and it'll be on the video.
Okay. Yeah.
Bye-bye.
All right.
All right. So if you're watching this on the video right now, go ahead and hit pause, give yourself a few minutes and take time to work these reactions. And when you're done, come back. I'm going to go ahead and work through them slowly here on the key, so you can watch it slow or you can just go to the end, whatever you want to do. I'm not sure of the solubility of this. I seem to have a memory of barium bromide not being soluble, but I'm not going to go look it up right now. Just if you want to, you can look it up. For this one, we do have a solid. We haven't seen many bases be solid, but zinc hydroxide is insoluble, and you can do that. You eat, Rolaids or Tums when you have heartburn, so that's putting a base inside your acidic stomach, so it's fine. Okay. A lot of 2s here in these examples. So again, a solid perchloric acid, not commonly used in these equations. If you've forgotten, perchlorate is part of Cash and G as the first C chlorates. Yeah, a little thunder going outside. Hopefully it'll rain. A solution of always means aqueous. All right, another solid. So that'll give us copper 2 chloride, which is aqueous, and more water. So water's in every one of these, water and a salt. So that'll be 2 and 2 again. And that will do it. Each one of these are neutralization reactions, but in fact, they're only actually neutralized if you have equal moles. And we will crack that nut maybe next week or the time after. All right, well, that wraps up tonight's lesson. We dove into acids and bases, got the bulk of what an acid and base is down. Next week, we'll visit pH and what that means, and maybe some stoichiometry after that. All right, see you next week.